What institution is it?
University of Essex.
University of Essex. So I'm very pleased to welcome David Penman to the University of Essex to talk to us today about randomly coloured graphs.
Okay, thank you. This is an old talk to a large extent, or at least part of it is an old talk, though I will update the talk, so to speak, to reflect more recent developments. A lot of the work, though, emanates from my PhD thesis, which was supervised by John Biggins and Chris Cannings. I'm not going, because it's 2 o'clock on a Friday afternoon, to get too bogged down in technicalities. I hope, at least, it's going to be a fairly elementary introduction. Let's begin, so to speak, at the beginning, which, as a wise man said, is usually a good place to begin. The usual random graph GNP, average range random graph. Each pair of vertices are adjacent with some probability p, which might very well depend on your number of vertices, and everything in sight is independent. Which, of course, is a very nice thing if you're doing probability calculations. You can't do calculations in probability unless you've got some kind of independence built in somewhere. There's a slight snag with all these nice calculations, though, which is that, very crudely speaking, reality isn't always like that. If you're working in this Erdős range random graph setting, now, standard sins that get committed in this game include, but are not restricted to, the following. Very often, I shall say that some property holds for a random graph, when what I really mean is it holds with probability tending to 1 as n goes to infinity. Which is frequently abbreviated WHP for with high probability. You can easily show that all the vertices in an Erdős range random graph, let's say for the moment that p is a constant, just to keep this kosher, have roughly the same degree, and of course they're independent of each other. There are a lot of real graphs out there that aren't particularly like that. I mean, if you think, for example, of a graph in which the vertices are various people and there's an edge between them if they're friends, people have found in practice, so to speak, that a friend of a friend is more likely than a person rounded up off the street at random to be a friend of the first person you started from, so to speak. And this is actually, to a large extent, what motivates the definition of these clustering coefficients that Steve Noble was talking about last week. Now, there are all sorts of fixes to this. You can take the sort of Matthew Penrose approach where you stick points into some real geometric space and some kind of, okay, so you chuck down points uniformly at random in some space, and you say that two of them are adjacent if the distance between them in some suitable norm you've specified is at most blah. And then you ask how the graph arises, and there's correlation there, of course, just because of the triangle inequality for your norm. All sorts of other approaches too. Steve Noble was talking about these web graphs and things like that. The approach here today is going to be slightly different. Now, when I was first doing this thing, I called this peculiar feature I'm going to introduce on the vertices a hidden colour. Colour is in some sense a slightly unfortunate way of putting it, because in some sense colour suggests that you can see it. And in some sense, part of the point of this is that you can't really see these colours. So each vertex is randomly going to select one of, it'll be finite in our examples, colours. Now, while we're talking about this here, we're all meant to know about physics nowadays. The idea that occurred to me is that it might sensibly be possible to say that you could regard this random colour as a sort of random spin for your vertex, in some hidden sense again. And what we'll say is that if I've got a vertex of colour I and a vertex of colour j, an edge between them will arise with probability pij. So if you've got k colours, there will be a k by k matrix of these pij's, and because we're talking undirected graphs, it will be a symmetric matrix. Now, what we're going to do with this graph, we're going to compare it and contrast it, so to speak, with a random graph gn alpha. Now, alpha is going to be the overall probability that an edge arises in this model. So, I mean, if you get colour I with probability si, then the overall probability that the edge arises is, by a very simple calculation, the sum over I and j going from 1 to k of the si times pij times sj. Just do it, so to speak. That's the overall probability that the edge arises. And what we're going to do is compare this graph with the gn alpha and see how they differ, or are similar in some cases, as we'll see. You should interrupt, by the way, at any point if things become unclear, which they almost certainly will. Let's make sure that we've grasped this basic idea. This is the sort of toyest case of this sort of thing that you can have that isn't just Erdős-Rényi. Two colours, red and blue, say. Okay? Each vertex independently tosses a coin. If it comes up, fair coin. If it comes up heads, I decide I'm red. If it comes up tails, I decide I'm blue. Okay? Red to red edges arise with probability P, blue to blue edges arise with probability P, but blue to red edges arise with probability Q. So, well, let's work out the probability that these three vertices, 1, 2, and 3, form a triangle. Well, it's very simple. In 2 of the 8 possible colourings, you could get all the vertices are the same colour, so the probability the edges arise is P cubed. In the other 6 cases, you've got 2 of one colour, which gives a P, and the other vertex is the other colour, so the other 2 edges are Q squared. Manipulative algebra. Okay, what is the probability alpha, the overall probability? Well, 2 cases where the 2 ends are the same, 2 cases where they're different, is this. We've already made our point, though. The point is that this is not just this number to the power 3. The edges are no longer independent of each other. So I do want to come back to this point about the colours being hidden, so to speak. I mean, conditional on the colourings, everything is independent, albeit with inhomogeneous probabilities still. But when you don't see the colours, you're looking at things in monochrome or some such phrase, these things are not independent. Clear? Okay. I should put some of these slides at least on the one over here so that you can keep a rough track of what's going on if we get behind later. The slides are meant to be numbered. Okay, let's have some formalism. I'm only going to talk in this particular talk about the case where k, the number of colours, is fixed, though I'm sure that cases where you allow it to go off to infinity or whatever with n as well would be interesting. And I mean, we shall see when I talk a little bit about some of the more advanced topics later on that people have begun to push that assumption. Anyway, so the colours are 1, 2 up to k. The probability that you get colour I is SI, so these SIs are non-negative, because the probabilities and they add up to 1. So it's a multinomial distribution. So you will get roughly n times SI vertices of colour I under normal circumstances. Probability that an edge between a vertex of colour I and a colour J arises is Pij, and as I say, conditional on the colouring, everything is independent, albeit with these inhomogeneous probabilities. So P will be a symmetric k by k matrix. Alpha, as before, will just be the weighted sum over all the possible choices for the colour of one end and the colour of the other end of the probabilities. The Erdős-Rényi model is, of course, a special case of this. If you just take Pij to be the same for all values of I and j, it's rather degenerate. And I mean, there are some other slightly degenerate cases. I mean, for example, if an SI is equal to 0, that's a wheel turning idly. But this is what we'll talk about. So there are, I suppose, 4 parameters here. N is the number of vertices, k is this number of colours, S is this k vector, which specifies the multinomial distribution, and P is a k by k symmetric matrix. So, for example, the GPQ model that we had in the last slide, just to help fix ideas, well, N is just left fixed. There are 2 colours here. The vertex S is equally likely to be the one or the other, and P is this symmetric matrix with little p in the diagonal and little q everywhere else. History of this, I mean, like a lot of these things that evolved, a number of people doing it at different times. This is from my thesis, the basics of it, and we had a paper about this by Chris Cannings and myself, which came out in 2003. Simultaneously, more or less, and unknown, I think either group to the other, Bo Söderberg, a physicist at Lund, had started thinking about these things. And he had at least a couple of papers about this came out at roughly the same time. Okay. Now, I mean, a lot of this stuff could be construed, so to speak, as being sort of correlation inequalities in some sense. I mean, as I understand it, is one of the themes of this workshop. you're going to sort of ask, how does this funny correlation structure that we've got affect the probabilities of various things happening as compared with what would happen in GNP? Sorry, I'm getting behind on this business of keeping things up to date. Right, now, so I mean, suppose I'm thinking about a particular tree. You know, it might be the tree with vertices 1 to 8, 8 to 47, and 47 to 6 million. When is it true that for any tree T, probability that all the edges of T are amongst the edges arising? Now, I mean, I'm using this slightly Baroque wording just to emphasize that I'm talking about the probability that all these edges are arising. I'm not insisting they arise as an induced subgraph or anything. I just want that all these edges arise. Well, sometimes it's just equal to what you would hope it might be if they were independent. Sometimes it is equal to this number, despite what we had in the previous slide. There's a very simple condition. This is not a difficult theorem. I've called it a theorem, but it's pretty straightforward, follow your nose stuff. If these numbers are, well, I was going to say constant. Strictly speaking, you only need them to be constant in the cases when SI is non-zero, but that's a technical aside. So, I mean, GPQ is a model of this sort because you can rapidly check in GPQ that you will get the same number, P plus Q over 2, for all of these sums here. The interesting question in some sense is what happens when the probability isn't equal to what it would be classically. I mean, this is a precise statement. Yeah, well, the other thing to note here is that you can work out whether this is going to be true or not just by looking at the passive lens 2. You don't really have to worry about all the trees. Just the passive lens 2 will sort it out for you. What if they're not equal? Well, the interesting fact that seems to be true in all cases we've done so far, and I mean, we'll see that this is not yet fully proven by any stretch of the imagination. Well, it's proven in the case of trees, but a generalization we'll come to is far from being proven in general. All the edges arise is at least what it would be in the classical situation. So it could only make the probability more likely, the nature of the correlation structure, in this case. Now, that's slightly surprising to begin with. Perhaps let's put this up first of all. Let's bin this. And let's go to the next slide. Now, I mean, when I first came across this stuff, I was doing it in ignorance of this important conjecture by Sidorenko, which is very relevant to it, as we'll see. Let B be a bipartite graph. Now, so far we've talked about trees. I'll talk about my situation in bipartite graphs of a more general sort in a minute. If you've got a fixed bipartite graph and some other graph with, let us say, n vertices and an average degree Pn, P will be a constant here, then Hom of G semicolon H is the number of homomorphic copies of G in H. So number of images of the graph under graph homomorphism. This is, so to speak, an obvious lower bound. This is roughly the number of them you would expect to get in the random graph. And it's also essentially the same as the number of copies, because the number of the homomorphisms which are not injective is in the nature of things going to be small. So this would imply that the number of labelled subgraphs of the target graph, the image graph H, which are isomorphic to your particular fixed label bipartite graph G, is at least this number. So if you think about it for a minute, you'll see that the truth of Sidorenko's conjecture for trees, now the truth of Sidorenko's conjecture for trees has been known for quite a long time. It was proved, perhaps not wholly surprisingly, by Sidorenko. The minute blue question mark here is simply to reflect the fact that in the paper by Chris Jagger, Pavel Stovacek and Andrew Thomason, which gives an alternative proof, they apparently noticed a sort of flaw let in the proof. I don't think there's any serious doubt that Sidorenko genuinely knew what was going on, so to speak, in the case of trees. And so it is true for trees. And you can see that implies the result for the conjecture that I was making a minute ago. Because if you've got that it is this number here, this is going to be the right number. And you couldn't have it being significantly less than that, because if it was the classical probability minus epsilon, then just for a big enough n, this is going to fail. Let's put this over here. Now, I mean, while I was still ignorant of Sidorenko's conjecture, I had proved it very easily for stars. This is a sort of one-line proof, basically. This is the formula for what would happen with a star. You condition on the colour of the central vertex of the star. You've then got each of these probabilities for the various other things, and it's just convexity or something. It's easy. It's also true for paths. That boils down to a slightly peculiar inequality concerning matrices with non-negative entries, which is called, amongst other things, the Mulholland-Smith inequality. I suspect it must be known in other contexts under other names too. The original context was apparently genetics or something. Well, okay, when you finish telling undergraduates about trees, the next thing you tell them about is cycles. What are we going to do about cycles? Let's work out the probability that some cycle, it might as well be 1, 2, 3 up to r to 1, because all vertices are equal in the sight of God, so to speak. They may get up to funny things on Earth due to this random colouring process, but it might as well be this. Well, here's the probability. You just put down all the possible colours for the, oh dear, r's have become n's at this point. So all n's on this line are r's. They've been sorted out mercifully further down. Not at immediately the most tractable looking things. The trick, which took me a little while to see because it's not terribly probabilistically natural, but it works, is just to put vi to be the square root of si, and qi will be root si times pij times vj. Now, take one of the root of si1s away, then you've got the other one, the pi1i2, and a root of si2, so that's a qi1i2. The other root goes with this one and a square root of si3 here to give you this, and so forth, all the way around. And at the end, of course, we mop up our remaining square root of si1 to go with this one. So these are all going together, okay? This, of course, is just going to be the trace of q to the r. Just do the matrix multiplications. Q is symmetric, and so there's no difficulties about this. This is the sum of the i's powers of the eigenvalues. Okay, some of these eigenvalues. What can we do with that? Well, of course, we can say something semi-intelligent about the biggest eigenvalue. By the Rayleigh principle, the biggest eigenvalue is the maximum over vectors of norm 1 of W transpose QW. And of course, V is a vector of norm 1 because it's got the square roots in. And so that's an upper bound of this, so this is at least alpha. So suppose that R is even, we've got a cycle of even length, then this thing here is, by the formula I just gave you, this, and that is at least as big as alpha to the R. Now, that argument obviously falls over when you allow R to be odd, because of course there can be, and indeed always will be, some negative, essentially always will be some negative eigenvalues here. And actually, the example for GPQ that we had already shows this as well. If Q gets bigger than P, so you're, so to speak, redistributing the mass of your edges and you're veering off in the direction of being bipartite, and of course bipartite is the same as no odd cycles, so in some sense it's not a surprise that it's getting harder to find odd cycles in it. This is the formula, so if Q is bigger than P, this is smaller than classically. So sometimes you get bigger, sometimes you don't. Even cycles are always at least as big as classically. And in fact, more generally, this is a simple exercise really. You can show that the probability that in GPQ is always exactly this, just either by specializing the general formula or just doing it by hand is frankly easier in this case. So all even cycles at least more likely, but all odd cycles less likely than classically. Now, this is actually sort of first pushed at me by Colin McDermott when he was examining the thesis. He said, you know, you've got these results here about the trees and the cycles. Why not make your conjecture the initial version, for more general bipartite graphs, because it works for even cycles, it works for trees. Why not try to push it through? So this is the generalization of my conjecture, and I hope you can see that Sidorenko's conjecture is still going to be relevant if you can get Sidorenko to work. Then this is still going to give you a result on this. Trouble is that Sidorenko's conjecture appears to be extremely difficult. We know it. Sidorenko proved it himself for even cycles and for complete bipartite graphs, and I think hacked out a way of doing it for complete bipartite graphs in my format too. More recent result on this is for a class of graphs including hypercubes by Hamid Hitami, who is one of Mike Malloy's students in Toronto. I'm going to say a little about that in a minute because there are some interesting links with other parts of mathematics, but it's very far from being known in general yet. There are a lot of cases that we still don't seem to know about. Part of the reason why I'm going to say something about Hamid Hitami stuff is that, again, there do seem to be some links with physics going on here. So I think most of the physicists are actually away today, but let's stir the pot anyway, so to speak. Right, so again, we've got homomorphisms from a graph G to a graph H. We're going to look at this thing here. So for each vertex of the starting graph, the one that you're having a homomorphism from G to H, remember, as the notation, you've got to decide where that vertex go to. So you've got to have a vertex in the target graph that it's going to. There are, of course, lots of terms in this summation here. And then you've got to have, if there's an edge between the two things in the starting graph G, there's got to be an edge between them in the target graph H, because it's a homomorphism. A here is going to be the adjacency mark of H, so you've got to have ones here where there was a one before. I am informed by those who know about these things that this is related at least to something called Mayer sums, which appear in statistical physics, and that also there are some things called Feynman sums in quantum field theory, a subject disclaimer about which I know absolutely nothing, which are, again, similar in format to this thing here. Now, it's actually convenient to work in a slightly more general context. The adjacency matrix here is a symmetric matrix, so let's just deal with more general symmetric matrix indexed by this index set I here. Okay? So this is a function that, given a graph G, you can define this function. Now, it turns out that in the particular case when you look at C4, and you take this function to the fourth root of it, that is actually a norm, just in the sense of functional analysis, on this set of symmetric matrices. Not an easy thing to prove, and perhaps not immediately obviously a relevant fact. But this is actually tying in with all sorts of other things that are going on out there at the moment. For example, most of you probably heard, at least in outline, about all this stuff by Tao and Green about the primes having arbitrarily long arithmetic progressions and things in them. And all that depends on buckets of use of various forms of the semi-radial regularity lemma. Terence Tao has an exact formulation of the regularity lemma in terms of one of these norms. And Tim Gowers, I mean, there's a lot of talk in some corners of the world about what are called Gowers norms these days. Has got footnotes too. So I mean, this fits in with other things. It's not just a kind of off-message freak thing, so to speak. Let's define a slight variant of the norm. All I'm going to do is I'm going to take the modulus of the entries of this matrix W that we were having. So instead of just the entries, I'll have the modulus of them. It's not going to make any difference for most of the things that we'll see in practice, where H is a bipartite graph with this given by partition. Now, what Hitami proves is that this thing here, which isn't a norm yet, I mean, it's wanting to be a norm. The notation is almost too leading at this stage. It's suggesting this is going to be a norm, but at the moment we haven't proved that. If and only if our bipartite graph H is what he calls weakly Hilder. And he managed to prove that hypercubes are weakly Hilder. So that is an addition to our rather limited range of graphs for which Sidorenko's conjecture is true. Why is that true? Well, this is a theorem that was pointed out to Hitami by Balazs Segedi. This, I think, is a spin-off from the work by Segedy and Lovaas on limit objects for graphs, the sort of sequences of dense graphs and so forth that there's been a lot of work on recently. If this thing here is a norm, then a non-trivial generalization of Sidorenko's conjecture is true for the graph H. Now, before you get too excited about this, Hatami is very clear that there are cases where this thing will not be a norm. I mean, for example, if you are a tree but not a star, then this thing is not a norm. So you're not going to get a sort of complete all-singing, dancing proof of Sidorenko's conjecture just from this idea. You're going to need some further ideas as well. But it's another case of these things, and because this is a more recent thing than most of the other ones, I thought it was worth saying a little about. Yeah, I'll skip that slide because time is slightly wearing on. It's not terribly important. Now, we are, unfortunately, even though it's 2 o'clock, we'll need 2:30 on a Friday afternoon, going to have one proof before we're finished. And it's going to be of this, which again sort of fits in with this sort of correlation inequality theme that we've got running through the workshop. Let's go back to our friend GPQ, where P is bigger than Q. Okay? Now, we've seen that in that case, this formula for a cycle, which I mentioned before, it's easy, as I say, to generalize, to derive from the general formula or just to hack out by hand, is given by this. Because P is bigger than Q, whether or not R is even or odd, this is always at least as big as alpha. Alpha, remember, is P plus Q over 2 in this model. The overall probability in edge arises. So, okay, trees in GPQ have the same probability of arising as classically. All the cycles are at least as likely. Can anything be less likely to arise in GPQ than classically? Now, the answer to that question is no. And we'll not only say that, but we will prove it. And in fact, we'll prove a somewhat more general statement. Suppose that Ci is an event that this particular bunch of edges arise, and C2 will be a similar event. You know, all these edges arise. Again, I insist, we're not insisting that these arise as induced subgraphs, just all these edges arise. Certain edges arise. Okay? So what we say is that the probability that both these events happen is at least as big as the product of these. This is getting a bit kind of like an FKG inequality. I'll make some remarks at the end to slightly dampen that down. I don't think it's quite as simple as that, actually. I'm going to give the proof of this. This proof is peculiar. If someone has seen a proof like this somewhere else, I shall be delighted to hear about it, because at the moment it's slightly kind of one-off and not making terribly much sense. So for doing the proof, we'll assume to begin with that, now I'm using slightly sloppy language here, the edges in C1 and C2, which is what we're really concerned with, there's no edge in common to them. We'll also assume that Q is greater than naught. These are technical assumptions to get things to run through, and we'll discard them pretty easily at the end. We'll say that Si is the number of edges in the configuration Ci whose endpoints are the same color in the random coloring. Okay? Call it the number of non-switches. And Ni will be the overall number of edges in Ci. Okay? Well, what's the joint probability? The probability of C1 and C2. Well, of course, you have to get, because they're edge disjoint, you have to get the S1 that are non-switches in C1 to arise, you have to get the S2 and C2 that are non-switches to arise with probability P, and you have to get the other edges, which are obviously switches, to arise. Let's just fiddle with this a little bit. There's nothing deep going on that line, just manipulative algebra. Is that the technology misbehaving? We'll assume that the technology is now behaving again. In a very similar way, you can get this formula for the probability of Ci here. It's exactly the same idea. Let's have theta being this quantity here. Now, because Q is strictly positive, this is finite, and because P is bigger than Q, it's positive. We'll use that fact in a minute. And so this is now a formula for the difference between these two things. Remember, this is the expression we're trying to prove is positive. Okay? So Q can be forgotten about, and what we're reduced to proving is this statement at the bottom here about, this is really a statement about two moment generating functions, I suppose. Hi, is there any problem with what happened with the microphone? It's okay, thank you. Oh, he's up to his old tricks again. This should be going over here. It's out of order now, never mind. Am I one slide has gone. Walkabout, what's happening here? Oh, no, it's not called walkabout, phew, right. What we'll do is we'll have C2 star. It's going to be the same graph, isomorphic as a graph to the edges that were in C2, but we're going to move it to some distant corner of the graph where there aren't any edges or vertices in common with C1. And so S2 star will be the number of non-switches over in this C2. Okay? As we saw at the bottom of the last slide, it's effectively equivalent to proving this inequality here with S2 star now. So I could put the S1 and the S2 star together now because C1 and C2 star are independent of each other because they've got no vertices in common. Okay, we all know what the Taylor series for an exponential is, and because theta is positive, it's enough to show this inequality in the middle now. I should use this pointer they've been kind enough to give me. Yeah? If we can get this fact here out, we're home, using the fact that theta was positive. Now, as you would guess, it's going to sort of boil down to sort of some indicator functions. We just number the edges in. It doesn't really matter what way. It's just a sort of tool we have to use. S1 is the sum of the indicators that gives us S1. So this indicator is 1 if that edge is a non-switch, and it's 0 otherwise. Similarly down here, similarly here. Okay, in addition to knowing the Taylor expansion, we all know the binomial theorem. We can expand this out, and what we've really got to prove is this inequality star here. Okay. Now, I mean, we're almost there now, and I hope that some of you can more or less see what's going on already. The point is going to be, crudely speaking, that it's going to be easier to force things to be the same colour in this original configuration where they might have some vertices in common, though not edges, than it is over here where they don't have these things in common. That's essentially all there's to it. I mean, you have to sort of dress it up in working about the components and various things, but we're essentially home now. So, I mean, this is just saying what I was just been saying orally a minute ago, that if you look at it on the left-hand side, that's the one with C1 and C2, rather than the right-hand side, which is C1 and C2 star. There are extra cycles there, and it's easier to force things to be the same colour, which is the only way that the product of indicators will contribute 1 to your expansions. Okay? With two assumptions to get rid of. First of all, the assumption that they're not edge disjoint, that's very easy. If we use this formula when they have got edges in common, the probability will actually be bigger because we'll be double counting some edges in here. So we're introducing probabilities when we should have ones. And of course, Q equals naught. You just smooth out by continuity at the end. Now, as I say, I mean, that's... I mean, it took us a while to find that, certainly when I was working it out. And I'm not aware offhand of any argument that's really like that for proving this. We thought a certain amount about whether we could generalize this when we were doing it, but didn't find a non-trivial generalization. You can do sort of trivial things where, you know, you have wheel turning idly colors that, you know, crop up with probability 0 or something, but that's silly, so to speak. You want a substantive generalization and we're not seeing it. Just a sort of warning about sort of FKG type stuff and increasing events. If you have got these three events here, so this is a rhombus, I suppose, with one diagonal in it. So C1 is that 1 to 2 and 2 to 3 arise. C2 is that 1 to 4 and 4 to 3 arise, so the two diagonal bits. And C3 is that the diagonal from 1 to 3 arises. So C1 intersects C3 is that the top triangle arises, C2 intersects C3 is that the bottom triangle arises. If you were being tempted to do this in a kind of naive kind of FKG way, this is a salutary warning to you. It's not quite as simple as that. If it was just working in that kind of way, I mean, this is an increasing event, this is an increasing event. So So it's something to do with the form of this sort of, these edges are eyes. And I don't think it's quite as simple as the absolutely standard FKG format. Let's put this over here. Okay, so the next thing I want to say, we're doing okay for time, yes, a little about is large deviations in number of edges. Now, we use this kind of technology, or at least some of this technology, a lot in this subject. Let's first think what would happen in GN alpha. Suppose you're just counting the number of edges. Well, okay, even my undergraduates know what the mean of a binomial random variable is. And then you ask yourself, so small deviations about that, the usual order of magnitude, i.e. n, so to speak, square root of the number of edges is the central limit theorem, and the better of my undergraduates can just about quote that on their good days. What's the probability of being way away from the mean? This is a large deviation up there. Well, of course, we use this notion all the time in this area, Chernoff upper bound on these things. Exponentially small in, well, the number of edges it is in this context. And whilst we don't actually use this all that often in this context, most of the time in this game our preoccupation is just to show that something can't get out of control. So the argument goes roughly at the level of this is some polynomial junk that could obstruct things, but I've got a negative exponential, so I've killed you, In fact, this is the limit, so to speak. You can prove a similar thing, of course, for the left tail. I've talked about the right tail here being way out, well above the thing, but you can equally make similar remarks for being well below the expected value. Now, what's happening in our situation, if you stop to think about it, this is mood music, so to speak. I'll make some sort of formal statements in a minute, but I want to put the mood music across first, so to speak. The point is, in some sense, that there are going to be two ways you can get a large deviation now. You can do it the traditional way, so to speak, by having implausibly large numbers of edges, even if you did get a reasonably normal colouring. But there's another way you could do it, which is, so to speak, comparatively cheap. If you were to get a large deviation in the number of vertices of some particular colour, which is with only probability only exponentially small in n rather than exponentially small in n squared, is roughly the point, then, of course, more or less automatically from that, or at least the far and away the most likely behaviour, given that you've got that large deviation in the colours, will be for you to then get the implications of that, so to speak, on the edges. Even if they then behave typically, you will get an unusually large number. So you're beginning to chip away at this notion that, large deviation is always minus the number of edges or whatever it is that you're adding up. You can get it with this correlation structure on the slightly cheap. Not, I think, sufficiently cheap to upset the apple cart in most things, or dare say that someone might manage to dream up a case where you really do need the full force of e to the minus n squared times the appropriate function and upset things out. So, there are, crudely speaking, there are two large deviation theorems going on here. One is the one in n, depending on large deviations in the number of colours, and the other one is, so to speak, the more conventional, given what happened there, what's happening to the number of edges given that colouring. Now, large deviations is not really a kind of 2 o'clock on a Friday afternoon subject. It's messy and it's technical. I'm not going to go into all the details, but I will try to give you some idea of what's going on here. What you want to say is that the limit of the probabilities divided by an, I should have said, is going to be, well, the suitable normalizing constants that you divide the log of the probabilities by to get the function. What you want to say is that the limit is this function, but this is one of the respects in which the large deviation stuff gets rather technical, and you have to instead choose this slightly different wording here. Our friend I here is called the rate function, and quite often these constants, the ANs, are called the rate. And basically, this is saying that this is the function that controls things, but you have to use this slightly cautious and baroque wording to get this past the referee, so to speak. It's fiddly stuff. A rate function is said to be good if these beasts here, these beasts are called level sets, are compact. Well, let's first of all state the result that we proved. So when we're in a dense random graph, that is to say the probabilities, the Pij's are all constant, not decreasing with n, so to speak. We got a large deviation principle for number of edges, and of course you divide by n minus 1 over 2. So you can say more or less explicitly what the rate function is. There will be separate rate functions. Now we've had an alarming change in notation here from i's to phi's, but they're the same thing, sorry. The rate function will be the infimum of all the rate functions conditional on the colouring, so to speak. It's not wholly unnatural reason if you sort of think about it. This delta here is, so to speak, the simplex, all vectors with positive components that add up to 1. So what you're saying is that you get the rate function overall as an infimum over all these possible colourings that you could be having en route to it. This goes over here. And of course, as I say, there is also this regime based on just the colourings going wrong too. I mean, I haven't been explicit about it. Of course, if you're dealing with the you'll get things being infinite if you're not careful at times, because what's going on? Let me make a couple of comments about this. Well, 3 comments. First of all, I mean, if all these rate functions conditional on the mixture that you get are good rate functions, then so is the overall rate function. You want your functions to be good rate functions. It's a desirable feature for controlling the behaviour. Secondly, you don't actually need the full force of independent colours. All you need is that large deviations in the number of colours obey suitably well behaved large deviation principles. And finally, you can extract a sort of more general result about large deviations for mixtures, where, you know, it depends on some other parameter from this circle of ideas. What I want to talk a little bit about now, for a couple of minutes, is the more recent development of this stuff by Corbena, Dokuum, Ponza, and Peter Merters at Bath, and we'll get towards something which has some claims again to being statistical physics as we go down this slide. So what I talked about in the previous slide is what happens for a dense graph, where all the p's were constant, and so the natural thing to divide the number of edges by is n minus 1 over 2. This time we're going to look at a sparse random graph, so to speak, Gn C over n. Now, we seem to have reverted to Erdős-Rényi for the minute. I'll explain why the coloured stuff is still relevant in a moment. It is relevant, I can assure you. They gave a joint large deviation principle for the empirical colour measure as just, so to speak, the actual proportion that you get of each colour, which of course is not necessarily the same as the SI proportion that you theoretically would hope to be getting, so to speak. If you get a large deviation behaviour, you'll get different proportions of each colour. And the empirical pair measure is just the number of edges, one end of which is colour I, other end of which is colour J, and we divide by n to get rid of the dependence on number of vertices. Again, you can get a good and reasonably explicit rate function. Now, the sort of interesting feature for this meeting that emerges from that is this down here. Now, even I'm now got to the stage where I'm happy to believe that this thing here is a boring, old-fashioned, no additional free variables Ising model partition function, okay? Because you have a spin which takes one of 2 values, Q equals 2, so to speak, and you take this thing here, beta is an inverse temperature. We've seen this quite a lot of times in this meeting, one way or another. Again, it's actually slightly more general than C over n. It's such that n times the probabilities tends to C. Now, let's see what we're doing here. You form this, you generate a random graph GNP of n, okay? You form this thing for the graph that you generated, and then you take the expectation. I've spelled out here explicitly that's expectation with respect to the graph, because of course with colours floating around as well, you might be worried what exactly you were taking expectation with respect to, but it's just the graph at the moment. Here's this thing, take the log of this, divide by n, take the limit of that. You can now reduce that to an expression which is certainly not an expression for 2:45 on a Friday afternoon, but is just an optimization problem in 4 real variables. Now, let me see how I'm getting on with this Parliamo physics lark. Easing model, that's clear. It's a partition function. We're calling it the random partition function because the graph that we're putting into it is random. And this process here, I think I'm allowed to call annealing, yes? So this is annealed asymptotics for the random partition function of the Ising model. That sound not too unreasonable? Yeah, okay. Now, again, a result which seems in the surface not to have much to do with these coloured random graphs, but the second half of the slide will reveal all, so to speak. Suppose that you think about, again, we're doing sparse random graphs where, basically the probability is C over N. And you think about the proportion of the vertices that have got degree k, and you let this be the degree distribution, so to speak. Then again, you can get a large deviation principle for this, with again, a nice explicit rate function. And all this sort of spins out from the methods that we were using before for this. The point, though, is this. In order to get their arguments to work, these two guys have to use not just the Erdős-Rényi random graph to work with, but these coloured, randomly coloured graphs as well. There is a standard technique in this area called change of measure for these large deviations, which people use. And in order to get the change of measure argument to work, they really do have to use random graphs with a colouring, as opposed to just Erdős-Rényi random graphs to push the arguments through. Now, I mean, of course, the fact that their argument had to use this doesn't imply that there isn't a proof working just with the Erdős-Rényi random graphs. But it's interesting that this seems to arise in a reasonably natural way, so to speak, in this context. Okay, yeah, this should go over here. I want to say something now. I mean, very often when one's talking about random graphs, the sort of question one starts from is this business of giant components and things. Now, I mean, I'm not going to state the sort of full result by Bollebach, Janssen, and Reardon, which gives the full details of this. It's a rather technical result to state in anything like its full generality. But I will give the idea, which has been floating around for some time, and will state loudly that it's true, so to speak. But the technical difficulties of this are quite messy. How do you decide whether in the good old days, just going back to GNP for the moment, there is a giant component in your graph? Well, the idea is this. You start at more or less any vertex you like. You say that all the stuff that's at distance 1 from that vertex is the offspring of that vertex. The stuff at distance 2 is the grandchildren and so forth. You might be getting worried by now about sort of cycles and things, but the point is, very crudely speaking, that there are sufficiently few cycles in this sparse random graph to upset anything, and this branching process approximation, as we call it, can be got to work. So since it's got to do with the branching process, it really depends on whether the branching process has a positive survival probability. That remember, by your branching process theory, has to do with the expected number of offspring. And basically, if C is bigger than 1, you will get a giant component, order linear in the number of vertices. And if it's less than 1, you won't. You'll just get logarithmic size, Mickey Mouse size. Now, in the situation that we're talking about now, the branching process is, of course, a multi-type branching process. If something like this is going to work, you're going to have to use a multi-type, because if I'm a vertex of type I don't just have offspring, I have offspring of various types. If I'm a red vertex, I have red offspring and I have blue offspring, so to speak. While you're working your head around the notions of red offspring and blue offspring, let's push on, so to speak. You can check. And there's non-trivial work involved in this. I mean, the paper by Bollebach, Janssen, and Reardon, goes on for 100 pages or more. It's dealing with a somewhat more general situation than this. This result, again, Söderberg, in one of the papers he wrote, said this sounds like a plausible heuristic for this. But I don't think, at least the papers by Söderberg that I have seen, certainly did not give mathematical proofs of this fact by some distance. Now, the magic number C is, of course, now going to be replaced. You're going to have a matrix of probable numbers of offspring of each type, and basically it's a certain norm of that matrix. Again, if the magic number is bigger than a cutoff point, you will get a giant component, and if it's below it, you will not. So that gives you a reasonably satisfactory story about what's happening for giant components and things there. I'm obviously not giving the details, but I mean, that would be most of a seminar in itself, even to state the notation for these things. There may be some kind of application of this in relation to sort of modelling of epidemics and things. For the epidemic modelling, people talk about things like susceptibles and infective and removed models, which is a sort of standard thing that they talk about. And there's an older paper in relation to the GNP by Barber and Mollison, which shows that a process of that kind is effectively the same as the way that a random graph GNP grows. And they managed to use the standard known results, and of course I've only skimmed the surface of the known results about the phase transition in GNP, which is a very well developed and extremely extensive story in what I'm saying this afternoon. They get it all to work out. So this kind of situation, I mean, there would be technical details to worry about, but it may well be that, you know, if we've got differing degrees of genetic susceptibility to catching this disease that's floating around, that you can model that reasonably sensibly by this kind of multi-type random graph. And, you know, if I've got the gene that makes me very resistant to it, if the bug is passing around, I probably won't catch it from people of various kinds. So you could possibly do that kind of thing if you're interested in that sort of thing too. Well, okay, I mean, this is obviously only a kind of introductory overview of it all, but I hope I have at least given you some idea of some of the things about this, and hopefully I've managed to stimulate at least some people who know about physics to think about this as well. Thank you.
Sound as if it's not a PIJ, but just a PJ, so probability that I am susceptible to an infection that's floating around.
Well, I mean, in some ways it won't be though, because I mean, if the bug gets into an individual of type I's system, I mean, the probability that it will be there enough, so to speak, to do damage could well depend on his type as well, so to speak.
Yes.
Before we, you know, I mean, the contacts are arising as some Poisson process or something, I don't know exactly.
This
Yeah.
growth model seems to suggest that perhaps the PIJ shouldn't be the same as PJI necessarily.
Yeah, certainly, I mean, there's always going to be a worry in relation to these things about directions on the edges, so to speak. I mean, it turns out that if you start with directions in the Barber and Mollison stuff and push that along, and then it's something that you can effectively forget about. It's just the graph of who's been in contact and how much the disease has spread that matters. But I mean, one of the kind of technical points that you would have to worry about if you were trying to do this for the multi-type situation is different starting points, so to speak. So I mean, I don't think it would make any serious difference, but you would have to do some bookkeeping at least to keep that sort of thing under control.
These normal talk last week, the models he were looking at were kind of generated recursively. He was adding vertices and joining to previously existing vertices with certain probabilities.
Yeah.
Is there a version of that using these coloured, hidden colours?
Well, I mean, you could sort of uncover the vertices of your graph, so to speak, one by one. You know. So we start off with, we've got at a certain point two certain vertices which have got certain colours and deform certain edges amongst themselves. A new vertex comes along, it tosses one of these k-dimensional coins, so to speak, decides what colour it's going to be, and then you can evolve it gradually. Is that what you're saying? You can evolve it gradually, but of course you'll have to bear in mind that the colours of the quotes previous close quotes vertices are already determined. So, but you can evolve it gradually, yes.
And would it be a better model for the World Wide Web and Steve's?
Well, I mean, that sort of depends on what the World Wide Web's really like, which is too big and complicated for me to know. But I mean, I think the feeling is the reason why people got involved in Steve's kind of models for things like the World Wide Web is because of this idea that when you're setting up a website, so to speak, you're as unimaginative as everybody else. So you include links to Google and the National Rail Timetable and your department's own web page and, you know, things that are already popular just because everyone else does so, so to speak, and you're a herd animal like everyone else. So that's why you've got this kind of preference for vertices a big degree that crop up in some of these models. This kind of thing, I mean, is not going to be a kind of realistic model of the web in that sense. I mean, it's going to be, this kind of thing is going to have exponential tails, whereas you'll remember the people who do these web graphs, they talk about these power law tails, which is a different ballgame to a large extent. So I mean, I don't think this is going to be a terribly kind of realistic model of the World Wide Web, no. But maybe something else. Hi.
Is there any extension to continuous valued graphs? These all, you're looking at binary edges.
Right. What do you mean by continuous valued graph, so to speak?
So you have a continuous, a set of continuous random variables, and there's some correlation that exists between those random variables, and that correlation is determined by, say, a hidden variable.
Do you want like
A Gaussian mixture model, for example. So this would arise in genetics when you're trying to relate to transcription factors that say evolve over some time period. They may not be correlated perfectly, correlated negatively perfectly. You may have some partial correlation that lies between -1 and +1. So you no longer have a binary relationship.
Degree of relationship, so to speak. Pass, I think, is the first round answer to that, because I mean, you're talking about things I haven't really thought about in the past, but I'll be perfectly happy to talk about it and see if one can make sense of it. But I certainly have not thought about graphs where, you know, there's a degree of adjacency or otherwise. I mean, I thought of in a nice simple world where things are either adjacent or aren't adjacent, but it may be that it's possible to do something like this in that context too. Okay.